This is summary of impedance obtained for a purely resistive, purely inductive, and purely capacitive circuit. So for a pure resistance circuit, the impedance Z is the ratio of the voltage across it, denoted as VR, divided by the current IR. Now we know that for a pure resistance, the voltage and the current phasors are in phase, that is the phase difference is 0, and this ratio is equal to R. The unit will be ohms. For a purely inductive circuit, the impedance Z is given as the ratio of voltage across the inductor divided by the current flowing through the inductor. Now we know that for a purely inductive circuit, the voltage is ahead of the current phasor by 90 degrees. So we can write this as VL by IL angle 90 degree. Now this ratio VL by IL is written as XL, which is also known as the inductive reactance of this circuit, and which can be written in the phasor domain as j omega L, that is JXL. So XL is omega L, which is 2 pi FL. The unit will be ohms. For purely capacitive circuit, the impedance is given as the ratio of the voltage across the capacitor divided by the current flowing through the capacitor, that is VC by IC. Now we know that for a purely capacitive circuit, the voltage is lagging behind the current by 90 degrees. So we have written here minus 90 degrees. The ratio VC by IC is also known as XC for the circuit, that is known as capacitive reactance. So XC angle minus 90 degrees, which can be written in this format as minus JXC. XC is 1 upon omega C, that is 1 upon 2 pi FC. The unit will remain ohms. Here we have written minus j omega C. So minus j omega C, the meaning is it's actually minus j upon omega C, or you can write this as 1 upon j omega C also. Let us now analyze the AC through a series RL circuit, that is a circuit consisting of resistance and inductance in series. So in this circuit, we have drawn the supply voltage. The values which are written here is V, capital V, that is denoting the RMS value, and the capital I is also the RMS value. The current and the voltage vectors for this resistive element has been shown here. Both are shown in phase. For an inductance, the voltage is VL across this and the current flowing through this is I. So we can draw vectorially the relation between the two current and the voltage across the inductor, with voltage is ahead of the current by 90 degrees. The equation for the voltage drop across resistance VR is written as IR, and VL, so voltage drop across inductor, is I times XL. If we want to write the equation of the supply voltage and the current in terms of the instantaneous values, and these will be the equations that can be written. Let us make the vector diagram for all the voltages which are there in this circuit. So we can draw it on the real and imaginary axis, as this is the current phasor, and the voltage is in phase with VR is in phase with I. So both are plotted here. The voltage VL is ahead of the current by 90 degrees. So we can plot it VL here. The resultant of these two voltages, VR and VL, is denoted as capital V, that is the supply voltage V. So we can write from this vector diagram, the resultant voltage V is actually the vector sum of the voltage VR and voltage VL. So this will be the magnitude of the resultant voltage V. Now VR is IR and VL is IXL. So we can write the formulas here to get this formula for V is equal to I under root R square plus XL square. Now if you look at this term R square plus XL square is equal to Z square, or I can write this entire thing as Z. That is called the impedance of this circuit, right? The Z is the impedance of the circuit. The unit will be ohms. So what I can write is I can write impedance square is equal to resistance square plus the reactance square, right? Now from this triangle, voltage triangle, the name of this triangle is voltage triangle, and this is also very important for analyzing and solving these type of networks. So the voltage triangle, we can write tan phi is VL by VR. In the triangle OAB, we can write tan phi is VL by VR, which is IXL by IR. So this gives us IXL I and I are crossed out. So we have XL by R, that is omega L by R, that is reactance by resistance. Or we can write phi is tan inverse XL by R. We can also write the relation for V from this voltage triangle in terms of the real and imaginary components as VR, V is equal to VR plus J times VL. Okay. Now this impedance Z, we can see these two equations, which are our instantaneous equations for the voltage and current. And because of the inductance in the circuit, we know that the current will be lagging behind the voltage by some angles phi and not 90-degree, right? Because the resistance is also present, so this phi will not be equal to 90. This will be some different value. Now the ratio of this Vm by Im is called the Z of the circuit. We can also write the impedance Z as the ratio of Vm by Im, or here I can write the maximum value of this current is given as Vm by Z. Also from both the equations we can clearly see that there is a phase difference between the two and the current is lagging behind applied voltage by phi. Now let us make one more triangle that is called the impedance triangle, and this triangle can also be drawn on the real and imaginary axis where R will be plotted along the real axis, that is along the current direction, and the XL component, that is the reactive component, will be drawn by 90-degree from this current. So we can draw here XL. So we are drawing it on imaginary axis, so we are writing as a JXL, which is J omega L. So, and the resultant of these two is called the Z, right? So the resultant of these two is Z. So from this impedance triangle, again we can write an expression for Z as R plus JXL, where R is denoting the real part of this impedance, which is resistance, and the second component is indicating the imaginary part, and which is giving us an indication of the reactance of this network. Now in this network, the reactance is XL, that is the inductive reactance, because the inductance is connected. So this is an inductive reactance. This is called the rectangular form of representation of Z. In the polar form of representation, we can write Z is equal to Z angle phi, right? Now also we can write the angle phi from this as tan inverse XL by R, this one. Now if I look at the expression for Z, and I can write the components of Z as R and XL in terms of Z as R will be Z cos phi and XL will be Z sin phi, which we obtained from this impedance triangle. Now here we can write V as Vm angle 0 and the current we can write as I is equal to Im. The angle will be minus phi. Also in the impedance triangle, we have seen one more parameter, that is if you take the cos of this angle phi, this is equal to R by Z. This cos phi, this entire cos phi, this is called the power factor of the circuit, right? So we can say that power factor is the angle which we have obtained from the impedance triangle. And if we look at the voltage triangle also, we can write the power factor, which is the cosine of the angle between the voltage and the current, that is a supply voltage and this current. So angle, cos of angle, this cos of phi, this is also known as power factor, which we can obtain from voltage triangle. And from impedance triangle, we can take the ratio R by Z. This gives us cos of phi, which is called the power factor. Now power factor is a measure of how effectively the incoming power is used in the electrical system. High power factor will indicate that the power supplied to the system is effectively used, and the system with low power factor will indicate that the power is not effectively used or consumed, and it may result in the losses in the system. The value of this power factor will always lies between 0 and 1. Okay, and when we write a power factor for any of the circuit, this we are writing the power factor we are defining for the AC circuits. So When we write the power factor, we'll have to write the words lagging and leading also. Lagging, leading, or we'll call it unity power factor. Okay, lagging, leading, or you can write this as unity power factor. I'm writing in short UPF, that is the unity power factor. Unity power factor will be obtained for a purely resistive circuit when both are in phase, V and I are in phase. And if for this type of circuit, this is an RL circuit, we can clearly see that the current is lagging behind the voltage. So whatever power factor value we are getting, we'll be writing here the word lagging, right? Instantaneous power for the series RL circuit can be obtained as the product of instantaneous voltage into instantaneous current. So we have substituted the equations here for the voltage and current to get the instantaneous power P. So it is consisting of two terms we can find. One is the constant term, other is the pulsating or the fluctuating term. And it is pulsating at double the frequency of the voltage or the current wave shapes. The average power consumed over the complete cycle, which we can obtain by integrating this from 0 to 2 pi. So that gives us 1 by 2 Vm cos phi. Vm are the maximum values of voltage and current respectively. So we can substitute Vm by root 2, Im by root 2 to write the expression for the average power consumed over one complete cycle, P equal to Vi cos phi, where V and I are the RMS values of voltages and currents. The unit of this power is watts. This power is also known as the real power, P, denoted by capital P, active power, or the average power. Also, sometimes we call it true power. Now the current. This is a voltage triangle. If you look at the current, current can be resolved into two components, I cos phi along the in phase with V, and the quadrature component, that is I sin phi, with 90-degree difference from the voltage. So there are two components of the current, I cos phi and I sin phi. I cos phi is called the active component. I sin phi is called the reactive component. Active component also known as in-phase component. Reactive component also known as quadrature component. The other names which are given to these components of the current is I cos phi is also known as the wattful component, and I sin phi is known as the wattless component. So there are two types of components for the current. So we'll call it wattless, that is I sin phi, and this will be termed as I cos phi will be termed as the wattful component. Now based on these two components, we'll be able to evaluate the expression for the powers. So let us see for this case, for an RL circuit, power is, we have already obtained here Vi cos phi. So Vi cos phi, how we can read this is, these are actually the product of Vrms into Irms into cos phi. Also we can read this as voltage multiplied by the component of the current which is in phase with it, that is I cos phi, that is the wattful component of the current. So and cos phi is also known as the power factor. So we will see that in the RL circuit, it is only the resistive part which is consuming the power, right? In case of the purely capacitive or purely inductive circuit, we have seen that the average power over the complete cycle was 0. But in case of resistive circuit, we have some power consumed, and same because this was an RL circuit, so we'll have a power consumed here. So that power consumed is Vi cos phi. Now, what we can write here, cos phi. We know from the impedance triangle, this cos phi can be written as R by Z. So we can write Vi multiplied by R by Z, which gives us I square R. The unit is watts, right? So formulas to calculate the power consumed in any AC circuit, which is consisting of resistance, inductance, capacitance, the power consumed will be obtained using this formula Vi cos phi. Or we can write I square R. So you can see in this formula we are getting R. So this R is indicating us that the power will be consumed by the resistive part only. So the active power is P equal to Vi cos phi. The unit is watts. This is also the product of voltage with the wattful component of the current I cos phi. This is the active power, the real power. So real power is also, you can say, it's the average of the instantaneous product of voltage and current that we have obtained, and it represents the capacity of electricity for performing work. The power which is supplied to the equipments in a power system that performs a useful and productive work. So it is it indicates that. So this is also called the wattful power. That is the product of VIRMS into IRMS into cos phi, that is the power factor. Now, if we have the product of voltage with the another component of the current, that is I sin phi, and if we multiply the two, that is VIRMS into IRMS into sin phi, then we will be getting the another power. The name of this power is the reactive power. The unit is volt amperes reactive, VAR, and this is also called the wattless power. That is the product of voltage multiplied by the wattless component of the current. That gives us another power. The name of this power is reactive power. The power which is required by equipment such as transformers and motors to produce the magnetic field or the flux, enabling actual work to be done. So this power is used to serve actually the magnetic flux in alternators to produce electricity by moving the conductor shaft of the turbine in the speed. The unit is volt amperes reactive, also known as wattless power, also known as wattless power. So the reactive power basically transforms no net energy to the load. The energy which is transformed to the load is indication of the active power. So the wattless power does not perform work. It is essential for maintaining voltage level in the system and ensuring that electrical equipment operates correctly. And in power systems or in electrical engineering, if we see, managing reactive power is crucial for stability and efficiency. The wattless current happens in purely inductive or capacitive circuit. That is the I sin phi component. Because in a circuit where there is only a capacitor or inductor, power dissipation becomes zero, even though the current is flowing through it. So when simply an inductor or capacitor is connected in a circuit, the power consumption is zero, and the current is known as the wattless current, as it consumes no energy in the circuit. So for an RL circuit, we can see that we have defined two types of power, active power and reactive power. Now there is one more power that is known as the apparent power, and it is denoted by capital S. So and that is given as V into I. The product of VRMS into IRMS gives the power S, and which can also be written as I square Z. The unit is VA, volt amperes. So the three types of powers which we can see is the apparent power, the active power, and the reactive power. So apparent power is I square Z, the active power is I square R, and the reactive power Q can also be written as I square XL. That is due to the inductive part or the capacitive part of the circuit, that is the reactance X. So we can write this as I square X, and also we can see here that this Q is same as VI sin phi, P is same as VI cos phi, and its unit is VAR. So we have three powers, so we can make a triangle known as the power triangle, where S is the resultant of these two powers, P and Q. So in this power triangle, on the real imaginary axis, we have drawn the power P, which is the real power or the active power on the real axis, and the Q is plotted with a 90-degree from this real axis, and S is the resultant of these two. So I can write from this triangle S square is P square plus Q square. So that gives me the magnitude of the apparent power from this triangle, which can be written in complex notation as S is equal to P plus JQ. Also, this power S can be obtained by this formula VI conjugate, that is the product of VRMS into the conjugate of the IRMS value of the current. Now from this triangle, we see that there is an angle phi has been indicated. If we take the cos of phi, this gives us the power factor. Means power factor you can obtain from all the three triangles that we have discussed so far, the voltage triangle, impedance triangle, and the power triangle. So in this power triangle, if I find cos phi, this comes out to be the ratio P by S, that is the ratio of active power to the apparent power, which is VI cos phi divided by VI. So VI cancels out and we have cos phi. So this is called the power factor of the circuit obtained from the power triangle. So the apparent power, we can see from this power triangle, the apparent power is the vector sum of the real power and reactive power. It is a very important quantity, the apparent power. Since AC apparatus such as generators, transformers is usually rated in volt amperes rather than in watts. The allowable output of such apparatus is usually limited not by mechanical stress but by temperature rise and hence by the losses in the device. The losses are determined by the voltage and current and are almost independent of the power factor. Thus, the amount of electrical equipment which are installed to supply certain load is essentially determined by volt amperes of the load rather than power alone. The rating of machine is defined as the maximum apparent power that is designed to carry continuously without overheating. In this circuit, the AC alternating voltage is supplied to the series combination of resistance and capacitance. The voltage drop across both the components is shown. VR is equal to IR, that is the voltage drop across the resistance, and VR is in phase with I. The second voltage drop which is across the capacitor is VC. So it's a drop across capacitor can be written as I into XC, where the drop across capacitor is lagging I by pi by 2. That is VC is lagging current by pi by 2. The vector diagram of both the components I and VR across R and VC and I across VC has been shown here. The voltage which is supplied to the circuit is written as the RMS, VRMS and IRMS. If we want to write in the instantaneous form, then we can write the supply voltage V in the lowercase v equal to Vm sin omega t and I equal to Im sin omega t plus phi. For the voltage triangle, if we draw the voltage triangle for this circuit, we can make the VR in phase with I. The VC is drawn in the negative direction and the resultant V is the sum of these two voltages VR and minus VC. So we can write V is equal to VR square plus minus VC square, and you can take a square root to get the magnitude of this vector V. So VR can be written as IR and VC can be written as minus IXC. So this is I multiplied by this term. This term is known as the impedance of the circuit. So Z is equal to R square plus X square square root, right? So this is the impedance of this circuit. The unit is ohms. Now we can make the impedance triangle as we have made in the case of RL circuit. So for RC circuit also we can make an impedance triangle, and this impedance triangle can be drawn. This is the real axis and this is the imaginary axis. So R will be drawn in phase with the this current I, and this is along the real axis. The reactance XC is drawn in the negative direction, so it's minus XC is written here. So we can write as minus JXC also. And the resultant of these two impedances, that is R and XC, will give us the total impedance of this network Z. So Z is equal to R minus JXC. The angle phi can be written as tan inverse minus XC upon R. In the polar form, the Z can be represented as Z. This is the magnitude of Z and the angle phi, where the magnitude is given by this expression. So we have Z and angle phi. Here we can see that the current leads the applied voltage by angle phi. So in the phasor notation, we can write V as Vm angle 0, and we can write the current as Im angle phi. So that is a phasor form representation of the current and voltage phasors. So we can utilize either the rectangular form or the polar form in order to carry out the analysis of such circuits. The instantaneous power over the series RC circuit can be obtained by the product of instantaneous voltage and instantaneous current. So substituting the expressions for these two, we arrive at the two components that we obtain for the instantaneous power. One is the constant component, another is the pulsating component. And when we calculate the average power consumed over the complete cycle from 0 to 2 pi, you can integrate this. So that will give us 1 by 2 Vm Im cos phi, which can be written in terms of the RMS values as P is equal to Vi cos phi. This P is called the average power or the true power or the real power. The unit of this power is watts. Now we can see that in RC circuit the power will be consumed only by resistance. So we can reframe this expression for the power P is Vi into cos phi. We know that from the impedance triangle the cos phi is R by Z. So we can write this as V by Z multiplied by I into R, that gives I square R. So that is watts. So P can be calculated, that is the average power or the real power can be calculated either using the formula Vi cos phi or we can use I square R. Now we have connected all the three passive elements R, L and C in series, and they are connected across an AC supply of RMS voltage V. This is the RMS current I. The voltage drop across resistance is VR and it is given as IR. This is in phase with I. VL is the voltage drop across L and it's given as IXL and it is leading I by pi by 2. VC is IXC, that is the voltage drop across C and it is lagging I by pi by 2. Here XL is omega L, which can be written as J omega L is equal to JXL, and XC is 1 upon omega C, which can be written as minus JXC or minus J upon omega C. Now the voltage triangle that is drawn here for this circuit, series RLC circuit, will be consisting of all the voltage vectors. So we are drawing VR with the real axis and VL, which will be 90 ahead of this. That is because it's 90 ahead of the current, which will be drawn in phase with the real axis. So on the imaginary axis, we are plotting VL and VC is minus, so it will be plotted in negative direction. But when we draw this vector minus VC here, then we get the vector A to D, which can be represented as VL minus VC. So in the vector notation, we can write the resultant vector V is equal to VR plus J times VL minus VC from this voltage triangle. Also, if you want to represent the voltages in terms of the instantaneous values, we can write V equal to Vm sin omega t and I is equal to Im sin omega t plus minus phi here. And we will be utilizing the plus sign when the XL is greater than XC, and when XC is greater than XL, then we'll be utilizing the plus sign. So I have here, because we have taken the assumption XL is greater than XC, so we can write I is equal to Im sin omega t minus phi. And in the phasor notation, we can write both V and I as Vm angle 0 and I as Im angle minus phi. Now in the voltage triangle, OD is OA square plus AD square. So that gives the magnitude for this voltage factor, which is OA is IR square and AD is IXL minus XC square. So that gives us I into Z. So here Z is given by this. So this is the magnitude of Z, that is R square plus XL minus XC whole square, and you can take a square root of this to get the final value of Z. This Z is called the impedance of this series RLC circuit. The unit will be ohms, right? Now we can make the impedance triangle. So impedance triangle, if we make, we can get this type of impedance triangle, which is plotted against the real and imaginary axis. So this is the R, which will be plotted against the real axis, and this will be drawn, the I has been taken as the reference vector, and JXL, that is 90 from here, from I. Similarly, Z is the final resultant of these two quantities, that is R and Jx. We'll call this as Jx, that is the net reactance, and this has been obtained when we are making this minus Jxe. We're moving in the is this in the upward direction, so this will be Jxl minus Xe from this point to this point to this point. So we have Jxl minus Xe. This is called the XL minus Xe is the net reactance of this circuit. The unit will be ohms. Here we have written XL minus Xe and not Xe minus XL because we have taken the assumption that XL is more than Xe. If Xe would have been more, then this net reactance will be Xe minus XL. So for this impedance triangle, we can represent Z as R plus JXL minus Xe, or we can write this is equal to R plus Jx, where the first term is called the real component of Z and the second term is called the imaginary component of the Z. So Z is having two components, R and Jx, where X is the net reactance. If we look at the angle phi, so phi will be obtained as tan inverse Xe minus XL minus Xe by R, that is tan inverse X by R. Power factor for this circuit will be obtained as R by Z, that is Z is R square plus X square, where X is XL minus Xe. So if I want to write the general representation of the impedance, I can write Z as R plus minus Jx, where the plus sign will be utilized when XL is more than Xe, which is the case here, that we have taken the assumption for this circuit that XL is more than Xe. So for this circuit, we have Z is equal to R plus Jx. And for if Xc is more than XL, then we'll be having here minus sign, right? So if suppose some value of impedance is given to me, suppose 3 plus J4. Okay, if it is a numerical, if we are giving the values of impedance Z is equal to 3 plus J4, then just looking at this sign, we can interpret that this might be having XL more, right? That is the nature of the circuit is inductive. So it is sometimes asked in the question that based on the impedance values that we get, uh, we need to write whether the circuit is inductive or capacitive in nature. So we can look at this sign, and this gives us an indication. If it is plus, that gives an indication that XL must be higher than XC, and the XL part is actually dominating. So we will call the nature of the circuit as more towards inductive side, that is inductive in nature. If it is minus sign, that means the XC part is dominating, and we will say that that might be the situation in this case, and when we have the J term minus, right? If we have this value of Z, then we will call this impedance to be capacitive in nature because we have this sign minus, right? So based on this sign, we can do an interpretation. Now, as far as the formulas for power is concerned for a series RLC circuit also, the formulas for P and Q will remain valid. P will be obtained in the same way as we have done for the series RL and series RC circuit. The power will remain. The formula for the real power P will be VI cos phi, and the power for the reactive power Q will be VI sin phi. The units will be, for the real power it will be watts, and for the reactive power it will be VAR, volt amperes reactive. Also from the power triangle, the power triangle will also remain valid for RLC circuit, where the resultant power or the total power is denoted by capital S, which is known as apparent power. The unit is volt amperes, and this is the vector sum of P plus JQ. Means what we can say that S is again having two components, P and Q, where the real component is P and the imaginary component is Q, that is the reactive power. To write about the power factor, we can find the cos of phi, and that is R by Z, or also we can find this angle phi either from the voltage triangle or we can find it from the impedance triangle. So from the voltage triangle, the phi is tan inverse XL by minus XL minus XC by R. So this gives me phi. So now I can take the cos of this phi. So that gives me the power factor of the circuit. So whenever we are calculating power factor for any of these circuits, whether it's an RL, RC or RLC or any AC circuit, if we are defining the power factor, we need to mention the word lagging and leading or the unity power factor with that, right? So for this circuit, the case that we have considered for this series RLC combination, we have assumed that XL is more than XC, right? So I can see here that the nature of the circuit is inductive, and the expression for the current that we have written is I is equal Im angle is minus phi, right? So this sign of the angle of current decides the nature of the power factor also. That is, the power factor is lagging, leading, or unity power factor can be obtained by looking at this value. So here I can see it is minus 5. So minus indicates that the power factor is lagging, right? And this is the angle by which it is lagging. So the current is lagging here. For the resultant current is lagging with angle minus 5.